All right, so the next chapter we're going to talk about is electrophilic aromatic substitution, also known as EAS reactions. In this book, it is chapter 13. All right, that's where this information can be found. So why are we even looking at EAS reactions? Well, we're going to continue to talk about aromatic compounds and then understand the reactions that are occurring with aromatic compounds. And these aromatic compounds, specifically derivatives of benzene, are very important in biological and pharmaceutical molecules. One lab we would have done if we were allowed to meet was the creation of a sulfa antibiotic via EAS reactions. So what's important is that we're going to start with a benzene ring. Okay, and we're going to substitute one of the 6 hydrogens on a benzene ring with something else. Now that something else, as you can see here, could be a halogen, could be a nitrate group, could be a hydrogen sulfite group, it could be an OH group, it could be another carbon group, or it could be a carbonyl carbon group, also known as an acyl group. The key to this chapter is understanding that once I substitute my benzene ring with something else, I will either react faster than what benzene does, or I'll react slower than what benzene does. If I react faster than what benzene does, I am known as an activator when I'm added to the ring. If I act slower than benzene, then I'm a deactivator. It doesn't mean that the ring won't add anything else. It just means it'll be slower than benzene. Okay. So AR-H stands for our aromatic compound, specifically our benzene ring. And here is how we're going to get there. Okay. So some important things we want to look at: nitration, sulfonation, halogenation, Fiedel-Crafts alkylation. We'll also look at Fiedel-Crafts acylation and see why acylation is better than alkylation. All right. Okay, so we're going to substitute our benzene ring with some substituent depending on what we're going to react it with. You should know the reactants that are needed. I can't just add a nitrate group. In order to add the nitro group, I need to, mix sulfuric acid with nitric acid, all right? And we'll see this. So there's actually pre-steps to get to the substitution mechanism. So the general mechanism is seen right here, okay? First of all, it's electrophilic aromatic substitution, which means I'm going to need an electrophile, and the electrophile is what's going to substitute onto the ring structure. Okay, so if we're going to look at it on the board here, all right, and look at having a benzene ring. So I have a benzene ring. It has its 6 pi electrons. Well, 2, 4, 6. Okay. And it has hydrogens attached to all of them. We're going to focus on that hydrogen right here. I am going to have an electrophile. It's probably going to be bonded to some nucleophile that brings it to the party. That nucleophile is going to be there later for my hydrogen when it leaves, have something to bond with it. My double bond comes and attacks the electrophile. Okay. When this happens, that double bond breaks down. But I can't lose that aromaticity. So what happens is, by this bond, okay, so let's just draw it this way first to explain it. Right now, as we sit, I'd have a hydrogen and the electrophile. I'd also have a positive charge sitting on that carbon right there. Because this double bond, these electrons are used, this is now short. It's making 1, 2, and it has a hydrogen here, 3 bonds, so it'd have a positive charge. What's great about benzene is that these pi electrons back here will back up this carbon, and basically say, you don't have to hold the whole burden. We're here for you. Okay? We're here for you. So, we're going to establish the positive charge throughout the entire ring structure. Okay? So, after that occurs, all right, benzene doesn't really want to be like this, so whatever nucleophile, and on the slides it's represented by Z, whatever nucleophile brought the electrophile to the party basically attacks the hydrogen. These electrons come back in, and the ring is re-established with aromaticity, but now the substituted electrophile sits on the ring. Now, if you want completeness, over here somewhere, there's the hydrogen with the nucleophile, no longer with a charge. Okay. So the key to this whole thing is the fact that these pi electrons over here help stabilize that carbocation and allow it to disperse throughout the entire ring. The way I always say it is, well, we have a breakup, okay? These electrons left this carbon. This carbon needs emotional support, and these other carbons are here for the emotional support of this carbon losing these electrons. Okay. That's the general reaction, all right, for our EAS reactions. And it happens like this every single time, no matter what your electrophile is, no matter what the nucleophile is to pick up the hydrogen. Okay. The first step of the electrophile or pi electrons attacking the electrophile is the rate determining step. That's what RDS is. Once this is going, all right, then boom, the nucleophile is going to go in and rip that hydrogen off, and we are going to reestablish aromaticity. Okay. So let's look at some different mechanisms. All right. Some different mechanisms. Halogenation. Well, if I'm doing halogenation and I have either Cl2 or Br2 or I2 or F2, but we're really going to use only Cl2 or Br2 in our situation. If I'm going to do that, neither one is positive or negative because Cl2 up here is making a nonpolar covalent bond. So right there is a nonpolar covalent bond. Therefore, nothing has a partial positive, nothing has a partial negative. Therefore, my electrons does not, or my pi electrons in the aromatic structure do not see an electrophile. So we need this prep step. This prep step is important. We bonded to a metal chloride, okay, a metal halide. For chlorine, it's usually aluminum chloride, and for bromine, it's usually iron 3 bromide. Doesn't mean it can't be those, but that's what's usually used. So if you were doing a halogenation reaction, they were drawing it out, over the arrow you would see Cl2 plus aluminum chloride or something like that. By doing so, what happens is you create this complex that now has a plus and minus charge, a plus and minus charge. And then it's exactly like we just saw. The electrons attack the positive end, okay, essentially pulling off one of the chlorines. These electrons go back to make that chlorine happy. So it's getting this whole, and why isn't it plucking this one, and why is it plucking this one? Well, don't forget, if you look at essentially the electron diagram, all right, probability or cloud diagram, you would see that that positive charge is engulfing this whole area over here. So it's going to take this chlorine, these electrons are going to come back, and we're going to create our nucleophile, which will then attach the hydrogen. And the key is we reestablish our aluminum chloride, but we've attached chlorine. Now the same mechanism happens for bromine. Br2 does the same exact thing, except, like I said, the metal halide that's usually used is iron 3 bromide. Okay. And that's what this one is showing right here. We need that prep step to make a bromine a positive charge to be attracted to the pi electrons of benzene. Okay. All right. Iodine can be used. Iodine oxidizes. We really don't use iodine. The rate of reaction with iodine or amount of product that you're going to get out is very, very low. It can be done. Okay. But usually we focus on doing these with chlorine and bromine, and we usually get a high yield above 80%. Not saying it can't be done with the other two. It's just usually not chosen. For nitration, we need to use nitric acid. This is nitric acid if you don't see it, HNO3. They just draw it that way so you can see what's breaking down. We react it with 2 parts sulfuric acid. You get out the hydronium ion, the hydrogen sulfate anion, and our NO2 ends up being positive charge. So this phase here is needed, this first step is needed specifically to get that positive charge. Okay. Then the double bond electrons. Now, as soon as I have an electrophile formed, it's back to the same process. Volcano insurance, volcano insurance, volcano insurance here. Okay. So we're back to the same process. Electrophile gets attacked by the pi electrons from benzene. A nucleophile comes in and removes those hydrogens. Where's my nucleophile? Right here. Replenishing the sulfuric acid. And what you'll see from this point on, this is my nucleophile really coming in here, which they don't show on the slides. But what you'll see more often is the reason sulfuric acid is used as a catalyst is because we replenish it at the end, and the hydrogen sulfate ion is too bulky to add across anything. So it really, is a way to recycle it and get rid of it. And for those of you who end up going to take an organic lab, you'll notice that during your process of your reactions, there will be a point where it's like neutralize any of the leftover acid. Add sodium bicarb and vent and then separate or whatever it is. Okay. If it's not all used up. And this is showing exactly how it works. One key I want to point down here, which is going to be important when we do amines, is that with nitrobenzene, once we make it, we could essentially reduce it to form an amino group and make aniline. And that's going to be important in our process and how we're going to connect organic chemistry to biochemistry, reducing nitros to amine groups. All right, there's 4 steps in sulfonation. This is also important, so mark that down. There's 4 steps. First step is we take the sulfuric acid. It's going to create H3O+. It's also going to create HSO4- and sulfur trioxide. Okay. The SO3 is what's going to be added. This here. Now, I know what you're saying, but there's no positive charge. Why are the electrons being drawn to the sulfur? Here's the reason. Draw out the Lewis structure of sulfur trioxide. Notice that sulfur is going to be partially positive, losing the electronegativity tug of war with oxygen. Okay. So SO3 gets added, but now there's something different. In the last 2 we looked at, halogenation and nitration, we added a positive, and the positive got canceled out by the electrons. This time, by adding a no charge to it, it now picks up a charge. This right here. We got to get rid of that charge. Our second step, all right, is to add the sulfur trioxide. Our third step is to reestablish aromaticity. Okay, just like we normally would. And we would be done here with our EAS reactions, but then what happens? Okay, we need to get rid of that negative. That negative isn't really great, so here comes H3O+ from up here that we created. The negative will attach and take one of the hydrogens, creating water. So if you want to break it down, one of these hydrogens essentially gives the electrons over to oxygen, and we create water. So there's an important fourth step that after we've substituted, after we've regained aromaticity in sulfonation, we have to get rid of the negative charge. So we're not just adding an SO3, we're actually adding a hydrogen sulfite group to the benzene ring. Key being the sulfur is added to the ring, not the hydrogen or the oxygen. Another big key is, see how these reactions are very reversible? This step, once it happens, not so reversible. Again, for the 7 of you that are watching, if you have any questions about this, but once you get the things down, like what has to be present to create my electrophile, it is the same process over and over. Okay, and this is breaking it all down for you. Here's a sulfonamide, and we're going to talk about how to create, wow, I've got 2 substituted things on the ring. How does that work? And we'll talk about that in a little bit here. Okay, Fiedel-Crafts alkylation, all right? Mixed acylation with alkylation there. Alkylation, okay? This is adding a carbon group to the chain. In order to do so, I need to react my carbon chain, which is usually an alkyl halide, with a metal halide to prep it. Okay. So let's say this is up here, I don't know, propyl or 1-chloropropane. Yeah, let's do that. 1-chloropropane. All right. And so this would be FeCl3, and we would combine to get the R+. Now the same process would happen. The chain would add, aromaticity would reform, and the FeX4 would take the hydrogen off. But there's an issue with Fiedel-Crafts alkylation. Once I add a carbon chain, okay, once I add this, the reaction rate, okay, rate of reaction goes through the roof. Actually, a carbon is a benzene activator. And what that means is this, that once the reaction rate goes through the roof, I can't stop adding R groups. So I have no control over the reaction. I might substitute 1, I might substitute 2, I might substitute in 3 different spots, depending on bulkiness and things like that. And we'll talk about those in a little bit. So, although alkylation is great for adding your carbon chain and getting your carbon chain onto a ring structure, the problem is that we can't control the reaction. So I want to add a propyl group to this benzene ring. I might this way add 1, 2, or 3 depending on bulkiness and conditions. Okay. Now, another limitation to Fiedel-Crafts alkylation is I can only use alkyl halides. I can't use vinyls. And it will not work if the ring contains an amino group on it. So if there's an amino group or a strong electron withdrawing group, which we'll talk about in a little bit, this reaction doesn't work. And the biggest one is, again, this reaction can't be stopped. And that's what this is showing up here. Hey, I'm looking to add this chain here to the ring. So I add it. But the problem is I add another one, and another one, and another one, and another one, and another one. The other thing that's a problem is I can have hydrogen or alkyl shifts through the process and definitely not get the product that I want. So although alkylation is a good possibility of essentially increasing your carbon chain, it has a lot of pitfalls. So what can we do if we want to add a chain but we don't want it to be something like this? Well, what we can do there, okay, is add an acyl group. And the difference between adding an acyl group and an alkyl group is this. Okay. An acyl group, all right, once it adds to the ring, all right, decreases reaction rate. It decreases the rate of reaction, which in turn means that we can control the reaction. It slows it down. The next substituent doesn't add super fast. Since it doesn't add super fast and it's a deactivator, there is no reestablishment of the carbocation. Therefore, we don't have to worry about hydride shift. We don't have to worry about methyl shifts. We'll get 95% of our product, 90%. We'll get a large amount of our product. But what if I don't want the carbonyl carbon? What if I just want a carbon chain? Well, then you could reduce the oxygen using hydrogen or anything like that in the presence of platinum or palladium to add your hydrogens and reduce it. Okay. And that's what this is showing right here. So it's a way of, if I add an acyl group, it's a way of controlling it, and I'll use an acyl chloride or an acyl bromide. It's a way of controlling the reaction, adding a chain that I want lengthwise, and then reducing the oxygen. So yeah, there's an extra step, but I don't have to worry about control. All right. So once I substitute to my ring, there's two things we have to look at. Reactivity of the substituent, whether it's an activator or deactivator, and whether it's an ortho, para, or meta director. And what I mean by that is the following. If we take a look at the board, okay, and let's say I have my benzene ring, and I have an electrophile attached to it. Okay, we'll call it E1. Now, in my next step, I want to add E2. And the question is, well, where does E2 go? Does it go here? Does it go here? Does it go here? Does it go here? Or does it go there? It has 5 different spots it can go to. Well, where it goes is all determined by this substituent. And this is what we mean by orientation. This up here can be an ortho para director, or it could be a meta director. In addition to that, besides worrying about orientation, we'll also look at, does it react faster than benzene? Or does it react slower than benzene once the substituent is put on? This will be known as an activator. This will be known as a deactivator. Again, it doesn't mean that it won't react. It just means it reacts slower than benzene itself. Okay, so you're either going to be an ortho para director or a meta director. You're either going to be an activator or deactivator. What you'll see is that there's ortho para activators, there's ortho para deactivators, and there's meta deactivators. There's no meta activators. Okay. All right. So here's a reaction of toluene. All right. So we have toluene. We already have a substituent on. What I'll tell you is CH3 is an ortho, para, and it's an activator. So it's going to react faster than benzene, and it's going to send the substituent to the ortho, para section. So I'm going to get two products out, here and here. Same thing here, same thing here. Just understand what your substituent is going to be that you're going to add next. Nitrobenzene. Nitrobenzene, or the nitro group, is a meta deactivator. Oh, that was a terrible A. I went right into the D. So it's a meta deactivator. It's going to react slower, and it's going to put the next substituent in the meta position. So the question is, well, how can I tell if I'm an activator or deactivator? How can I tell if I'm orthopara or meta? Well, there is a way to tell, okay? And the way to tell is actually looking at the substituent. So let's look at this line right here. If my substituent, that is bonded, okay, to the ring. Well, first of all, let me do it this way. Let's look at our halogens. Our halogens are classified as orthopara directors, but they react slower than benzene. Mark that up. Now, let's look at these over here. Here's the way to tell whether I'm an activator or a deactivator. And I'm not going to sit there and tell you, oh, which one's more of an activator, which one's more of a deactivator. I'm just going to ask you, is it an activator or deactivator? Is it meta or is it orthopara? Here's how to tell. If the substituent attached to the ring, O bonded to a carbon, nitrogen bonded to a carbon, nitrogen bonded to a hydrogen, oxygen bonded to a hydrogen, an alkyl group, R group bonded, like CH3. If the substituent that's bonded to the ring, if the atom in that substituent is more electronegative to what it's bonded to, I'll be an activator. So let's say this was CH3. Let me try to explain that a little bit better. Say that's CH3. Carbon is going to be attached to the ring. Carbon is more electronegative than hydrogen. It's an activator. Oxygen is going to be attached to the ring. It's more electronegative than carbon. It's going to be an activator. Nitrogen more electronegative than hydrogen. Oxygen more electronegative than hydrogen. Now let's go down here and look at the other side. Nitrogen bonded to oxygen. Oxygen's more electronegative. Therefore, it's going to be meta. Sulfur bonded to oxygen. Oxygen is more electronegative. Meta. C bonded to N. N is more electronegative. Meta. And so on. C double bonded to O. Double bonded O. Double bonded O. Double bonded O. Double bonded O. Okay. That'll make me be a deactivator and a meta due to it pulling the electrons, those more electronegative, pulling those electrons. A little inductive effect there. And halogens are always orthopara deactivators. So orthopara deactivators, halogens. Orthopara activators, more electronegative atom attached to the ring. Meta deactivators, less electronegative atom attached to the ring compared to the rest of the atoms in the substituents. This breaks it down for you to show where orthoparas are, where I rather be, how I rather be. So if I'm an orthopara director, I will have two products. That's definite. Okay. And this is showing why it acts that way. And it's all about being able to stabilize that carbocation in different spots. At the ortho section, at the para section, okay, and so on. All right. And again, showing it. And you could go through this. 4 resonance forms with the OH. Really not going to like meta because of I don't get 4 resonance forms. Same thing here. 4 resonance forms with chlorine. Rather be that than the 3 resonance forms. So more resonance, more stability. Okay, and then it shows it with the deactivating. Not going to be stable. All right. Not stable at para. All right, if we take a look at what your carbocation is and how many carbons it's bonding to. and then look at your carbocation in the meta position and see how many carbocations, all right, or how many carbons it's bonded to give the stability, and is what you're looking at here. Okay. Now, what's going to be important about this, and the slides go into it, but I'm going to show you on the board here, and you could definitely look at it, look at rings, look at how many we're going, what's going on, but be sure you understand order matters if you want to make a product. So what I mean by that is, let's say I'm given a benzene ring. Okay. I'm given a blank canvas benzene ring. And the product I want the product I want is, let's say that. And I say to you, create this compound. Show me in a reaction how you're going to create the compound. And the question is, well, what do you add first? Do you add the NO2 group? Or do you add the OH group? And the key is their location. They are meta to one another. Well, OH is an ortho-para activator. NO2 is a meta deactivator. Okay. So what do I want to add first? Well, if I'm going to do this correctly, have my benzene ring, I'm going to want to add my HNO3 and H2SO4 first. And you could draw out the mechanism. Due to board space, I'm not going to draw out the complete mechanism here. I'm just going to attach the nitrate. And then I could add my OH group, just like I would add any alcohol group. I could use water and H2SO4 if I wanted to. And where's it going to send it? Well, now that this is on, it's going to be slower, but it's going to add the OH group. And that would be the proper way to do it, because it's going to add it in the meta phase or meta place. All right. Now, if I did it the opposite way, and we added the water and H2SO4 first, and we added the OH group, and then we went to add our nitrate group, HNO2, and or HNO3, I should say, and H2SO4. We would end up with two products. One being the para nitrophenol, and we'd also have the ortho nitrophenol as our products. And that's not what we wanted. We wanted this. So order is important. So you have to sit there and figure out, well, what am I going to add first? What am I going to add second? What am I going to add third? And is it even possible to make said product? Now, what happens then if after I do this, I want to add, let's say, a third electrophile? Okay. What happens is that OH, now that it's attached, is the leader of the ring. So first the NO2 is leader of the ring. Now the OH is more, and this is where your list would become important of. But I don't make you memorize things like that you can go and look up. Like, there's no reason to memorize that OH is better than NH2, because if you were doing this reaction and trying to figure it out, you'd have that list in front of you. It's important to understand which are deactivators and which are not, so that when you are making something, all right, that we understand in what order they'll go. But to know which one's a better deactivator and which one's a better activator, I think that's a waste of brain space, in my opinion. But I'm sure someone will see this video and argue with me, and I'll just nod and smile. All right. So, OH takes over as the leader now. And we're going to be able to go ortho, or we're going to be able to go para. And we have a chance to go ortho there. Okay? Now, our products would look like this. From the way we started this, we'd have our NO2 here. We'd have our OH here. And we can add our electrophile there in the para position. We'd have another product here, NO2. Oh, not our NO2, sorry. NO2 is on top. Better stay consistent. OH. And our third electrophile, whatever it is, there. And we have another possibility. NO2. OH. Our third possibility is put the electrophile right there. Now, those are our three possibilities of our products. The problem is, this one will not happen. And if it does, it happens at such a small quantity. But it probably won't, because fitting in here, there's too much steric. And like I said to you, if you have me in Orgo 1, when everything is wrong and someone asks you in Orgo why something can't happen, always look for steric hindrance as one of your possible answers. To squeeze that electrophile in between an NO2 and a phenyl group, probably not going to happen. It would rather go here as ortho and there as para, even though that should be one of the options. Okay. So something to try for homework, and I'm just going to think of these. I mean, you could go through the book, and the book is going to have plenty of examples of this. But something to try for homework is, and again, I'm just making them up off the top of my head, so I don't even know if they're possible. So you'll have to figure it out and say, is it possible the way we know to make the following? All right. Show the mechanism to make this. Show the mechanism to make, and put them in the right order. What else one did we do? Yeah. There we go. Well, let's just do it this way so I show that the nitrogen's actually bonded there. NO2 like that. Okay. So see if you can draw mechanisms that show this, because this is exactly one of the questions or something specific like that where I'll ask on this next exam, hey, show me how you would do this. All right, in what order would you add these, subtract these, or, can it even be made? Okay. Can it even be made? Kind of thing. Okay. All right, let's move on. Any questions as we go here? So here, these are just showing you the reactions and what you could expect based on the functional group. So here we have an O bonded to a C, a more electronegative, so it's going to be an activator, so it'll be orthopara. Here we have a C with a double bonded O, it's going to be a deactivator, therefore, and it's going to be meta, we end up there. Bromine is an orthopara deactivator. It'll react slower than benzene, but it'll still go in the orthopara position. Okay. And this is just saying exactly what we just talked about and why. Here's another reactivity group if you want to look at it in another way. Okay. The group that is more activating will direct the next substitute. And that's what I'm saying. If you end up with two, orthopara activators on a chain, and you're saying, well, which one's going to go where? Who's going to direct what? It's whoever's the better activator. At that point, that's when you should pull out your list. But again, I'm not going to sit there and have you memorize which is the better, which is the worst. Okay. And that's what this is showing. All right. Now, the rest of this slides, there's like 10 of them left, is basically saying all the same stuff that we just talked about. So again, this is chapter 13 in the book. Go through it. I would understand the prep steps for each one of your different substitutions. I would understand activator versus deactivator, meta, ortho, para. I would also look at, again, order matters, which way you would make a multi-substituted benzene ring.